The sun ascends with a predatory grace over the vast, unyielding expanse of the Persian desert, a landscape where the horizon offers no sanctuary, and the atmosphere serves not as a shield, but as a magnifying glass for a star's untamed furnace. In this realm, the dawn does not bring the gentle warmth of awakening. It heralds the arrival of a structural force that threatens the very molecular integrity of everything it touches. No forests cast a softening shade to offer relief to a weary traveler, for the trees have long since surrendered to the arid wind. No vast mountain ranges break the immediate horizon to stall the advance of the solar radiation. And no rivers cool the radiant air with their moisture, as the surface water has been reclaimed by the sky in an eternal, thirsty cycle. For no clouds soften the blinding light that strikes the parched earth with a relentless, surgical intensity, turning the desert floor into a vast mirror of infrared energy. By midday, the temperature regularly reaches 50 degrees Celsius, a threshold where heat ceases to be an environmental factor and becomes a lethal condition of existence. Stone radiates like the interior of a kiln. The air shimmers above the ground in dizzying, cruel optical illusions, and exposed metal can sear human skin in a fraction of a second. Water left in a shallow dish does not merely sit. It vanishes into vapor before it can even soak into the parched earth, leaving behind only a white, crystalline crust of salt, as a grim reminder of the desert's hostility toward life. In such an environment, the presence of large-scale civilizations should theoretically be an impossibility. The biological limits of the human body, which begins to suffer systemic failure once the ambient temperature exceeds the capacity for skin-level evaporation, and the physical limits of standard building materials should have dictated a history of failure for any attempt at permanent settlement. Yet the cities are there, standing as monuments to human ingenuity. For more than 1,000 years, settlements like Yazd, Kerman, and Kashan have flourished in the very heart of the Iranian plateau, enduring the most extreme conditions on the planet. They do not exist there as temporary outposts or seasonal camps of nomadic desperation. They have been inhabited continuously, generation after generation, for centuries. This triumph over nature was not the result of mere luck, nor was it a simple act of stoic endurance. It was a crystalline form of integrated environmental engineering, a mastery of the invisible laws of the universe. The true wonder is not simply that the ancient Persians built shelters, but that they engineered entire urban ecosystems to survive 50-degree heat without a single watt of electricity, without a kilogram of steel, and without the aid of mechanical refrigeration. Their only tools were the humble earth beneath their feet, the geometry of shadows, the inherent physics of the wind, and the hidden, rhythmic pulse of deep underground water. To understand how these cities survived, one must first dismantle the nature of the enemy itself. In extreme desert climates, heat is not a singular force, but an assault from 3 distinct directions simultaneously. There is the direct solar radiation, a high-frequency energy bombardment from the sky. Then there is reflected radiation, or albedo, where the bright, sandy surface of the ground reflects heat back up toward any structure attacking from below. Finally, there is the most insidious form, accumulated radiant heat. This is the energy stored within the very fabric of a building during the day and released slowly long after sunset. A structure that merely blocks sunlight still absorbs massive amounts of energy. By the afternoon, such a building becomes a secondary source of heat, radiating infrared energy into the interior even when the sun is no longer visible. The solution to this triple threat began with a masterstroke of material science. While timber was a rare luxury, and stone was a heavy, inefficient radiator that turned rooms into ovens. The desert provided an abundance of clay. Sun-dried mud brick, known as kesht, became the foundation of survival. This was no simple mud. It was a specific composite of clay, fine sand, and organic binders like straw or goat hair, shaped into thick blocks and cured in the sun. From a thermodynamic perspective, this is a brilliant material, possessing high thermal mass and low thermal conductivity. In the walls of Persian desert homes, which often reached thicknesses of nearly a meter, this material created a phenomenon known as thermal lag. When the sun strikes the outer surface of a mud brick wall at noon, the heat does not penetrate immediately. The molecular structure of the clay absorbs the energy, but its low conductivity slows its progress to a crawl. It takes nearly 12 hours for this thermal wave to travel through the dense, earthen structure. By the time the heat finally reaches the inner surface of the wall, the sun has long since set, and the desert night has arrived. Because the night air is remarkably cold due to the absence of atmospheric humidity, the accumulated energy within the walls begins to release outward into the cooler night air, rather than radiating into the living space. The building does not fight the sun. It absorbs its fury and delays it, utilizing the very rotation of the planet to cancel out the extremes of the day with the cooling potential of the night. However, thick walls alone cannot solve the problem of air quality or the accumulation of heat in a sealed environment. To provide ventilation without admitting the scorching exterior air, the Persians developed the Badgir, or Windcatcher. These tall or rectangular towers rising above the city skyline are far more than status symbols or ornamental flourishes. They are sophisticated, multifunctional aerodynamic machines. A typical Badgir is internally divided into several vertical shafts, often arranged in intricate patterns to ensure functionality, regardless of wind direction. This internal division is the key to their operation. Even when the air at street level feels completely still, air currents are almost always moving at higher altitudes due to the pressure differentials across the desert plain. When wind strikes one side of the tower, it creates a region of positive pressure. The air is forced downward through the windward shaft and into the heart of the building, often passing through a series of internal chambers that slow its velocity. Simultaneously, but on the opposite side of the tower, the wind creates a region of negative pressure, which acts as a powerful suction mechanism. Hot, stagnant air from the interior of the house is pulled upward through the leeward shafts and expelled back into the atmosphere. This is the Bernoulli principle, applied centuries before the formalization of fluid dynamics. On days of absolute calm, the system undergoes a remarkable phase shift. It transforms from a wind-driven pump into a solar-driven chimney. The sun heats one face of the tower, warming the air inside that specific shaft. As the air warms, its density decreases, causing it to rise through natural convection. This stack effect creates a constant vertical draft that sucks cooler air from the lower, shaded levels of the house or from subterranean chambers. The building literally breathes, but maintaining a constant exchange of air that is self-regulating and requires zero moving parts. Yet, the most impressive feat of Persian engineering remains hidden from the blinding sun. While airflow and thermal mass can modulate heat to truly cool air from 50 degrees Celsius to a comfortable 25 degrees Celsius requires a heat sink. The Persians found this in the qanat, a vast, invisible network of underground aqueducts that represent one of the greatest engineering feats of antiquity. The construction of a qanat was an undertaking of staggering complexity. involving the tapping of deep aquifers at the base of distant mountain ranges and transporting that water across tens of kilometers of desert through a hand-dug tunnel. The gradient was the most critical factor. The tunnel had to slope at a precise angle, often as low as 1 meter of drop per kilometer of length. That if the slope were too steep, the rushing water would erode the tunnel and cause a catastrophic collapse. If it were too shallow, the water would stagnate or evaporate into the soil before reaching the city. The men who built these, the Muqanis, were the elite engineers of their day, descending into vertical shafts over 100 meters deep to reach the mother well. Working in cramped, oxygen-deprived conditions, they were guided only by the flame of an oil lamp and an intuitive understanding of geology. The genius of the qanat system is its inherent insulation. By moving water deep underground, the Persians protected it from the two greatest threats of the desert: solar radiation and evaporation. The water arrives at the city gates as cold and fresh as the mountain snows from which it originated. This water was managed by a mirab, a water master, who used intricate water clocks to ensure a fair and equitable distribution among the citizens, a form of social engineering as precise as the physical tunnels themselves. The qanat did more than provide drinking water. It was the primary cooling agent in the city's thermal system. In many Persian homes, architects built the sardab, a deep basement, or the payab, an access point directly into the qanat channel, when the hot, dry desert air captured by the Badgir is directed down into these subterranean chambers. It is forced to pass over the surface of the cold running water. Here, the laws of thermodynamics take full effect. Because the desert air is extremely dry, it has a massive capacity for moisture. As the air passes over the water, intense evaporation occurs. Evaporation is an endothermic process. It requires energy to break the bonds of water molecules, and this energy is drawn directly from the air itself in the form of heat. This process can lower the air temperature by as much as 20 degrees Celsius in a matter of seconds. The resulting air is not only cold, but also slightly humidified, providing a lush, cave-like relief from the bone-dry exterior. This dense, chilled air then settles in the lower rooms, creating a reservoir of coolness that resists the invasion of the midday heat. The individual house was only one component of a larger, integrated urban machine. Persian desert cities were designed with a specific thermal geometry that governed every street and alleyway. Streets were purposefully narrow and winding, rarely wider than 2 or 3 meters, ensuring that at almost any hour of the day, at least one wall was casting a deep shadow over the path below. This created a canyon effect that protected pedestrians from the full brunt of the sun. Many of these streets were covered by sabbats, arched vaults that bridged the space between houses and turned open-air alleys into shaded tunnels. As wind entered these narrow passages, it would accelerate due to the Venturi effect, increasing the rate of convective cooling for anyone walking beneath. The city was not a collection of isolated buildings. It was a system of interconnected thermal zones. At the center of the domestic world was the hayat, or sunken courtyard. Often located a few steps below street level, the courtyard served as a private microclimate. By planting pomegranate or fig trees and placing a central pool, the residents created a space where transpiration and evaporation worked together to lower temperatures. During the day, the courtyard held a pool of cool, heavy air. At night, the open courtyard allowed the building to radiate its accumulated heat directly into the cold sink of the deep sky. Architecture was in perfect synchronization with the Earth's rotation. Perhaps the most miraculous achievement of this era was the Yakhchal, the ancient Persian refrigerator. In an environment where the temperature could melt wax, the Persians found a way to store ice through the height of summer. The Yakchol is a massive mud brick dome, often 15 meters high, with a deep storage pit beneath it. The construction used a special mortar called saruj, a mixture of lime, ash, and organic fibers that was completely waterproof and highly insulating. But during the winter, water was channeled into shallow, shaded ponds behind massive shadow walls that blocked the low winter sun. On clear winter nights, the water would freeze due to radiative cooling, losing heat to the cold vacuum of space. The ice was harvested at dawn, broken into blocks, and packed into the Yakchol pit. The dome's shape was specifically designed to encourage any rising heat to gather at the very top, where it was vented out, while the heavy cold air remained trapped in the bottom with the ice. This allowed the Persians to enjoy chilled desserts and cold drinks, even when the desert outside reached its most lethal temperatures. Even light was a subject of engineering. Horsey windows with stained glass did not just play an aesthetic role. They filtered the harsh desert glare into soft shades of blue and green, reducing the psychological feeling of heat and the internal radiant load. Obivatale stayed in the lowest and healthiest layers of air, sitting on carpets placed directly on the cooling stone floors. The ancient Persian city was more than a triumph of survival. It was a masterclass in passive design and environmental intelligence. Modern architecture has largely forgotten these lessons, relying instead on brute force engineering, high-consumption HVAC systems that battle the environment rather than aligning with it. These modern systems are fragile, depending on a constant supply of electricity and refrigerants that further damage the planet and contribute to the very warming they seek to mitigate. When the power fails in a modern glass and steel desert city, the buildings become death traps within hours. But the ancient cities of the Iranian plateau were resilient, relying on the eternal constants of physics, gravity, the weight of the earth, the behavior of fluids, and the cycle of the sun. Every thick wall was a battery. Every tower was a lung. Every tunnel was a lifeline. This was not a primitive culture struggling against nature, but a highly advanced civilization that had mastered the art of soft engineering. They understood that the desert was not an enemy to be defeated, but a set of conditions to be understood. By working within the laws of thermodynamics, they built a world that could breathe, cool itself, and endure in the face of the sun's most punishing glare. As we look toward a future of rising global temperatures, the mud brick towers of Yazd offer a silent or elegant alternative, a reminder that the most sophisticated solutions are often those that require the least power and the most wisdom, transforming the harshest environments into sanctuaries of life and culture through the mastery of the invisible forces that govern our world.